Hi, everyone. Thank you for joining us for this virtual lunch discussion today. Please allow me to introduce CSAIL's Tamara Broderick, who will delve into some of her latest research. Feel free to send questions for Tamara in the chat, and I will ask on your behalf throughout the presentation or at the end as we see fit. And with that, please take it away, Tamara.
Hi, great. It's great to be here. I'm Tamara Broderick, and today I'll be talking about a check that you can run on your data analysis, namely a check to see if there exists a tiny fraction of your data that if you dropped it would change your substantive conclusions. Before I go on, I just want to highlight my amazing postdoc, Ryan Giordano, who's been working on this, and our fantastic collaborator, Rachel Meager, who used to be a PhD student at MIT and is now a professor at the London School of Economics. Okay. So in some sense, the question that we're asking today is, when can I trust my data analysis? The story of perhaps the past few decades is that as we get more data and better computation, that data analyses can increasingly drive life-changing decisions. So these could be in medical advances, they could be in individual medical care, they could be in cybersecurity, they could be in personal finance and financial policy writ large. And these would just all be cases where we really care about getting our decisions right, that we really want to make sure that we can really trust our analysis. Okay, now if I have a really important program, I don't want to just accept its output. I want to run tests to check that it's doing the right thing. And so we sort of want to ask, what are the tests that would be appropriate for a data analysis? Well, that's going to depend on the particular data analysis that we're running. And probably there should be a lot of tests, like not just one test. And so I'm definitely not going to be exhaustive today about all the possible tests that you might run, but I am going to try to suggest one test that should be pretty general purpose. That is, it should apply to a lot of data analyses. And in particular, the question that we'll ask about is, would you be concerned if dropping a small fraction of data changed your substantive conclusions? And today we'll talk about a test to see if there is such a small fraction of data. Okay, so why doesn't everybody already check this all the time if it's such a useful and important test? Well, it's just too expensive. I mean, it's astronomically expensive, and we'll go into this more shortly, to actually check if dropping any data subset would change your substantive conclusions. And so the work that we provide is a fast and automated and accurate approximation so that you can actually run this test in practice, whereas it wouldn't really have been feasible before. Okay, so just to whet your appetite for the rest of this talk, we see in a major published and influential study of microcredit with over 16,500 data points that there is one data point that drives the sign of the effect. If you drop it, you get a result of a different sign. That's the difference between microcredit helping people and microcredit hurting people. We'll learn a lot more about the details of that very shortly. Okay, so what are we going to get in the rest of this talk? Well, first, we're going to talk about why do we even care about dropping data subsets? When would you care about this in your data analysis? We'll talk about how should we drop data subsets? What is that going to look like in a given analysis? Why is it computationally expensive? Why can't we just do this brute force? Why do we need to do anything slightly fancier? And so we'll see, hopefully, that we want something at least a little fancier, and that'll be our fast and automatic approximation that will let us do this. And then we'll see it basically in practice in a lot of areas. We're going to see that many analyses are robust, but some are not. And that non-robustness in the form that I'm talking about today isn't something that you could just get for free from a lot of existing technology. You couldn't just say, oh, I've got these gross outliers, so I know what the answer is. Oh, I've got large p-values or small p-values, so I know what the answer is. Oh, I've got heavy tails or light tails, so I know what the answer is. These are things that people think about in a lot of other types of robustness. That's not the type of robustness we're talking about today. Oh, and then finally, we'll see that really it's a product in some sense of stability, of low signal to noise. Okay, so let's start by talking about when do we care about dropping data subsets? Why is this even something that we'd want to investigate in our data analyses? Okay, well, to start by answering this question, I want to first just make an observation about the way that people talk about robustness. So robustness, unfortunately, when people talk about sensitivity and robustness a lot of the times, and even probably earlier in slides in this talk, it sounds as though they're monoliths. Something is sensitive or it's not, something is robust or it's not. But really, it's always shorthand. What we really mean, and anytime anybody talks about sensitivity or robustness, is sensitivity to some change. And there are a lot of different changes in your data or your analysis that you could be sensitive to or you could not be sensitive to. And so somehow what we really want to ask when we're talking about sensitivity and robustness is what change is appropriate. Certainly there are some changes where I don't, where I get a change in my data that must be appropriate. If I were not sensitive to anything, that would be a really useless analysis. If I had a machine learning analysis that always returned the number 5, yeah, that's not sensitive to any change in my data. It's just not a useful analysis that I would ever run. And so clearly there's more nuance to the story than just being sensitive or robust. Okay, so what sensitivity concerns us will vary by problem. And so again, what I'm essentially doing on this slide is trying to convince you of at least one type of sensitivity that should concern us in certain types of cases. Now, to ground this in particular applications, let's look at economics. Why are we looking at economics? Well, one, it's a hugely influential discipline. It drives major policy decisions that affect all of our lives. Two, it's a fantastically reproducible field. And so we had an amazing time with this paper. We were able to reproduce the important papers and the analyses that were in them perfectly, down to like many decimal places. It was really fantastic. And three, prosaically, we were lucky enough to collaborate with a wonderful economics expert. That's Rachel Meager. And so these are the reasons we're thinking about economics. But let's ask, what do we learn from economics about robustness? Well, something that comes up in economics, and spoiler alert, all of these are not going to be specific to economics. But something that comes up is that in almost any statistical or machine learning method, you're typically reporting something that looks like a mean, and that's just not what you often want to learn from an analysis. So let's say, as an example, that I'm studying microcredit. So recall that microcredit represents these small loans to individuals in impoverished areas, and the hope is that these small loans help bring them out of poverty. And that's measured in various ways. Now, what I really want is to ask, is microcredit helping a lot of people? So maybe I go into a village, and in that village, it turns out that microcredit is hurting absolutely everybody. This is just a thought experiment for the moment. So it turns out that microcredit's hurting everybody. It's making their business profits lower. It doesn't help at all. But then suppose that Jeff Bezos walks into my village. He just happens to be visiting. And at that moment, I run my study and I ask everybody, how much did their microcredit or how much did their business profit change? Over the years that Jeff Bezos has been around. And it so happens that the business profit with Jeff Bezos is through the roof. I'm just asking, hey, do people in this village have a higher business profit now? And yes, it's super high. On average, the business profit is extremely positive. But if Jeff Bezos weren't there, it would be negative. It would be a negative effect. And so this is the sort of thing that we want to do, is we want to say, hey, is there this individual person who's driving a statistic like the mean? Can we get rid of that person? Can we get rid of the Jeff Bezoses from our data set? Another reason that we care about if there's a very small fraction of our data that's driving our conclusions is that in a lot of real life analyses, and certainly in economic analyses, small fractions of data are often missing, not at random. And so, for instance, if you have an analysis where you're calling up people on the phone to ask them, if something happened, well, you're going to miss all of the people who don't have phones. That's missing this not at random. These are, a biased set of your population. You're going to miss the people who don't want to answer on the phone, and so on. And so, just the way that you collect data often suggests that data is missing not at random. And so, you would like to not be, to not have your analysis totally depend on that fact. It is necessarily the case that a policy population is different from your analyzed population. So let's suppose that you analyze microcredit in Mexico and you'd like to establish, do some kind of policy based on that in the Philippines. Well, those are different places. Not only that, but suppose that you analyze microcredit in one place at one time. Well, now I want my conclusions to apply to 5 years from now. That's still a different set of people. And so if our analysis is extremely sensitive to a very small fraction of the data, it suggests that the conclusions we make are not going to be generalizable, that they're not going to apply to different cases.
Hey, Tamara.
Yes, please.
Question, what is the connection here to the outlier detection?
Yeah, so we're going to see a later example where you can get rid of outliers in a very common way that people would get rid of outliers, and you can still have a model that is, and an analysis that is sensitive to a very small fraction of data. And so one way to think about this is that you can have influential data points, not purely from at least some ways of thinking about outliers. outliers. Now, of course, if you think of outliers as being influential data points, I mean, this becomes tautologous and you're sort of getting rid of it. So you could also think of this as being a way of defining outliers. What's a meaningful way to define outliers? But you sort of want to take one of the two texts, and then we're going to see that these aren't quite the same. But yeah, I think there's some sense in which we're thinking, how much do data points influence our analysis? And here we're thinking for a specific analysis. And so again, depends how you define outliers there.
Like, I just got one more about why would profit increase? Why would the profit increase because of Jeff Bezos?
Great. Okay, so a typical thing that I might do is something like called a randomized controlled trial. And so what I would do is, let's say I would randomly assign this village to get microcredit and this village to not get microcredit. And then what I'm going to do is I'm going to look at the average profit in both villages. And so if I find that the average profit in the village that didn't get microcredit was $1 US, and the average profit in the village that did get microcredit was 1,000 US dollars, I might be like, man, microcredit's really helping people. That's like a lot more US dollars. Okay, now suppose that Jeff Bezos, who makes billions in profit, is in my village. Well, if I have 1,000 people and they all on average make like $1 US of profit, or let's say it's even like 0.1 in this case, because maybe microcredit was hurting people, and I just average 1,000 of those people with billions in profit, just because of the nature of the aspect of taking an average, that the average profit will be extremely high, even though everybody individually made less profit. And so this is just sort of in some sense, an observation about the nature of averages, that you can have things that are really far in the tail, and that makes it looks really bad. So you see this even in less extreme examples. If you look at things like the average profit of somebody in the U.S. or the average let's say amount that somebody in the U.S. makes, the average home ownership price in the U.S., all of these things are skewed by a large and heavy tail. If you look at the median of those values, it's typically much less. And so if you really want something representative of a full population, a median is typically a better way to go. One could ask, why don't we just put medians into things? So two observations. One, yeah, you totally could do that, and you should. But the default statistical and machine learning packages that like everybody uses do not. And so if you're using any kind of default and you're not making up your own like statistical and machine learning technology, or not being aware of this to start with, then this is going to come up. And then two, what about the problem you didn't anticipate? So I'm telling you one way it could be an issue that like, there was this one really unusual, influential person in your data set that changed your analysis. That doesn't mean there is no other way. This is just to illustrate that this is something that you should care about. There are many other ways that you could care about it. Hopefully that's convincing. This is a great place to be asking questions, by the way, because if we're not convinced that we want to drop data, the rest of this talk is going to be super uninteresting. So if there's any more, this is a great place to start.
Thank you. Yeah, we're keep going.
Okay, great. So hopefully we all are now convinced that in all of these cases, we'd be concerned if dropping a small fraction of our data changed our conclusions. And again, I want to emphasize this point. Oh, I didn't talk about models are misspecified. Let me just briefly mention here. Just every model that anybody uses in social sciences has to be misspecified because people are complex. There are all kinds of fascinating things going on in them. And these models are just not as cannot possibly be as complex as people. Okay, so now I want to emphasize that these concerns, none of these concerns are specific to economics. It's a nice illustration of why we care about them, but it's not specific. Models are misspecified in every discipline with possibly the exception of some areas of theoretical physics. They're just never perfectly right. It's always the case that you want to generalize your findings. This is like the point of science to something that you haven't seen yet. It's often the case that actually getting data is difficult and you don't get it exactly the way that you want. And it's always the case that like the default statistical and machine learning methods we're using tend to report a proxy for what we really want, and we should be aware of that. Okay, finally, I'll mention that this type of sensitivity doesn't have to bother you. There are cases where it might not. So for instance, suppose you're analyzing a city of 30,000 people or two cities, each of 30,000 people, and you're looking at murders in those cities, and there were 6 murders in one city and 3 murders in the other. Murders are clearly a rare event. They should definitely be a rare event. We hope they're a rare event. And so it should be the case that a small fraction of your data drives your analysis. But you should be upfront about it. If you're telling people that you're doing an analysis of murders, the relevant quantity isn't that you're looking at 30,000 people. The relevant quantity is that you're looking at 6 murders. And so effectively you have 6 data points, not 30,000. Okay, but there are many cases where we are concerned about dropping the small fraction of data. And so let's talk about those cases. Okay, how do we actually do this? So let's start adding a little notation. So we might worry if dropping a small fraction of our data changes our conclusion. So first, let's call that fraction alpha. It's technically between 0 and 1, but we're thinking of it as being very, very small. If it takes a substantial fraction of our data to change our conclusions, we're not worried because they got to change eventually. Okay, what does it mean to change conclusions? Well, it really depends on your analysis. So let me just give you some examples that many people care about. Changing the sign of an effect. This is the difference between microcredit helping people and microcredit hurting people. Changing the significance of effect. Here I'm talking about statistical significance. People will often say something like, oh, if microcredit it has a statistically significant effect, then I'm going to make some decision based on that. This is essentially, what is your decision-making criterion? Maybe it's if microcredit both is helping people and that's statistically significant. Maybe that's your decision-making criterion. Now, in all of these cases, we want to say some notion of, well, when are things bad? You know, when is this too sensitive? And so we might define something we're going to call a maximum influence perturbation. This is the largest possible change we can get in this quantity of interest, this quantity that defines our decision by dropping at most 100 alpha% of the data. So for instance, we could be interested in some effect size, like how much does microcredit help people? And we want to know if it goes from positive to negative. And we could look at that in this case by saying, let's say we only care about 1%. We'll choose alpha equals 0.01 and ask what's the largest change we can get? Can we change its sign if we drop at most 1% of our data? Our related quantity that we're probably super interested in, if we're going to do this analysis, is what is the data set that you drop to achieve the maximum influence perturbation? What I would probably recommend in any data analysis where you run this check, this check that we're describing today, is that you then find out what were those data points and you check, oh, Jeff Bezos was in my data set. I see what went wrong. And so then I'll decide to remove him. But otherwise, you could do something like, you know, it depends on what the person is. Maybe the person's a totally reasonable person and you actually wanted to include them in your data set. It depends. But you certainly probably want to look at this information. Okay, another piece of information you might be interested in is what we're going to call a perturbation-inducing proportion. This is sort of just a different way of looking at the problem. We want to say, hey, maybe there's a certain change we're concerned about, like changing sign of an effect. How much data would we have to drop to get that change? And if it's very, very small, we're not too, we're very concerned. If it's very large or there is no data that we could drop to change that, then we're not too concerned. We think it's very robust. Okay, so how do we get these? I mean, this is essentially it. This is the thing that we want to calculate. This is the test that we want to run. We want to find these things. If you only understand this aspect of the talk, you could kind of tune out until we get to the experiments at the end. Everything in between is just going to be about approximating this. Okay, so how do we find this maximum influence perturbation? Well, something you could do is just rerun your data analysis with every appropriate subset dropped. So let's look at an example of this. Suppose I have 400 data points. This is a pretty small data set. And suppose I'm interested in 1% of my data. I'm only worried if I have to drop less than 1% of my data to change the sign of the effect. So what am I going to do to check that? Well, I'm going to check dropping every 4 data points, because that's 1%. I'm going to check dropping every 3 data points, every 2 data points, every 1 data point. Let's just look at 400 dropping 4. Well, 400 choose 4 is over 1 billion. And so I'm going to have to rerun my analysis over 1 billion times just to check dropping 4 data points. If my analysis takes only a single second, which I think is optimistic for many data analyses, then this check is still going to take over 31 years. What if I have 16,000 data points? So this is, we're going to look at this microcredit study with over 16,000 data points. And let's make this an easier problem. I only care about dropping 0.1% of the data. That's even smaller. Well, then, by similar logic, I'm going to have to rerun my analysis over 10 to the 53 times. If my analysis takes 1 second to run, which again is optimistic, this check will take over 10 to the 46 years. I want to suggest that distributed computing does not solve every problem, and it will not solve this problem. It doesn't matter how much distributed computing you have, 10 to the 46 years is just not going to be distributed away. You're going to need some other way to run this check. And so this is why we need some kind of approximation. This is why we need some kind of algorithmic advance, because we just really can't run this otherwise. Okay, so that's what we're going to look at next. Now, before I tell you what that approximation is, let's look at it in practice. Let's see what happens. Was there a question?
Yes. Just going back to that, I just got in, why can't you just drop the specific data points? Why does it? Yes.
Yeah, okay, so here's a question. Why can't you just drop the worst case data points and see what happens there? Well, how do you know what the worst case data points are? This is the problem. We don't know what the worst case data points are. How do we find them? We could do an exhaustive search over data points, but beyond that, we're going to have to think harder. And so this is the part where we start thinking harder.
Thank you.
Cool. Okay, let's look at microcredit. So there's this beautiful paper from 2015, Angelucci et al., which has over 16,500 data points. This is the largest of 7 extremely influential randomized controlled trials examining the effect of microcredit. This is a wonderful paper. I encourage you to check it out. It's fantastically reproducible. They're great at sharing their data. I mean, really, I can't say enough good things about the economics discipline in all of this. So let's look at their model. Now, the first thing to notice is I'm going to show you a very simple model, and I'll say why we're not looking at a more complex model in just a second. Okay, so this simple model is just really simple linear regression. So here n indexes, little n, indexes a small business. That small business either received microcredit or it did not. And so we can have an indicator that tells us which it is. It's 1, xn is 1 if this business received microcredit, it's 0 if it did not. This is something we observe. So it's randomly assigned, but we know which one happened. The profit of each small business, yn, is observed as well. And then from these, we want to infer, from a classical linear model standpoint, what are these parameters, theta naught and theta 1? So theta naught is like the base business profit if microcredit did not exist. And theta 1 is the effect of microcredit. If it's positive, then microcredit's helping business profits. If it's negative, then microcredit is hurting. Now, it turns out you can do a much more complicated model than this with all kinds of covariates and lots of other things that people ran. And it just turns out it doesn't really change the conclusions. And so we're just going to look at the simple one. Okay, and by the conclusions, I mean like the actual microcredit conclusions, not just what we're doing here as the check. Okay, so theta hat 1 is the estimate that these researchers find, and we conclude as well. We're able to reproduce for the effect of microcredit, and they find it's negative US dollars purchasing power parity every 2 weeks, but with a really high standard error. And so a typical thing that you would conclude at this point is, yeah, it looks like it might be hurting, but actually this is well within the standard error, so it's not statistically significant, and so we just don't really know. And I'll come back to this point later. But let's first try running our approximation. So our approximation, first of all, takes 2 seconds to run, not 10 to the 46 years. And so this is something that you really can run in practice. We find that you can remove a single household and change the sign of the effect from negative to positive. So that's the difference between microcredit hurting again and microcredit helping. Now, I think very reasonably you might be saying, yeah, but it wasn't statistically significant to begin with. Well, we can remove 15 data points. So that's still less than 0.1% of the entire data set and get a statistically significant result of the opposite sign. So that's a completely different decision at that point. And so the thing we're observing here is that we can drop an extremely small percentage of our data and change our decision. Okay, it turns out we have lots of theory to support this, but I think something that's really great here is that you don't have to trust any of our theory. You can just look at the data points that we tell you are the problematic data points, because one of the things you get out of this is here are the problematic data points. Here are the ones that we dropped to get this change. And you can rerun the regression to check directly if that change actually happened. And so you don't have to trust the theory that goes into this approximation. You can check it directly if that's true. Now, some things we're going to see later are you might be thinking, well, maybe this is sensitive just because it was not statistically significant to begin with. We're going to see the opposite later on in another influential economic study. You might be thinking, oh, the issue is gross outliers. And we're going to see that that's not, you can get rid of gross outliers and you can still have sensitivity. If you're familiar with other common types of robustness that people talk about, you might think the issue is heavy tails. We're going to see that that's not decisive later on. Again, if you're familiar with other types of robustness, you might be thinking reporting means is the issue. That's not the issue going on. It turns out that you could take a Bayesian approach here, and our collaborator Rachel Meeker certainly has done that in her work, and that doesn't solve this either. I won't talk about that in the talk today, but it's in the paper if you're interested in checking that out, and I'll link that at the end. Okay, and the issue we're going to see is this notion of signal to noise. So I'm going to talk about this very briefly, but essentially signal is the amount of information we have about what we care about, and noise is what's making it hard for us to access that information. It's sort of telling us how stable of a problem this is. Okay, so at this point, hopefully we care about dropping data subsets. It seems like something that we want to do to check a lot of our data analyses. We saw that there's this brute force way to see what is the worst data analysis we could run. Where is the Jeff Bezos in our data set? But it's very expensive. And so we can't just run it directly. I mean, literally, it's just astronomically expensive. And so we're going to do an approximation instead. Okay, so now we're going to talk about that approximation. Again, it would be totally fine if you just understood everything up to here and then tuned back in for the experiments. But for people who are interested in the approximation, that's what I'll go over next. Okay, so before we go into that approximation, let me describe a very generic machine learning problem. So pretty generically in machine learning, you have a bunch of data. Let's say it's indexed by n. So little n goes from 1 up to capital N. And let's say dn is our nth data point. That could be in the form of supervised learning, where you have a set of features or covariates xn and a set of responses or labels yn, but it doesn't have to be. So for instance, if you're doing unsupervised learning, this would take a different look. This could be very generic, the data that you have. We typically also have a set of parameters. So the parameters are the things that we want to learn about in the problem that we don't know. We saw an example of this with microcredit. Sort of, we wanted to learn about, well, what's the business profit without microcredit and what's the microcredit effect? We have a loss that relates those parameters to that data point. Typically, we sum up that loss over all the data points to say what's the loss over the whole data set. And then a way that we will often estimate theta, we'll come up with a value of theta, is by minimizing that loss. And we'll call theta hat our estimator based on the data. Now, gosh, lots of things in machine learning fit this. Just about everything looks like a minimum loss. Also, you could look at maximum likelihood. That's going to look like this for negative log likelihood. You might be thinking, hey, I can think of some things that aren't quite like this in machine learning. Like what if I had a penalty, or what if I did an optimization and then I did a second optimization, like an instrumental variables regression. And actually, we can handle all of that too. This is just a very generic and sort of convenient way to write a lot of data analyses. So if you're interested in the full generality of what we can handle, check out the paper, but it does include things like penalties and multiple optimizations. Okay, but let's look at this setup again, because it's relatively straightforward. Yes, please.
Yes, just got another question in. Identifying specific data points to drop seems interesting and has a bit of an adversarial flavor. Is there a way to constrain the dropping analysis beyond just the fraction of data to drop?
Probably. I guess I'm curious if the question asker has anything in particular in mind. So I mean, I guess there's some sense in which we're going to see how this works very shortly. And so anything that can be adapted from that, absolutely. Something that would be, relatively easy to do is to say, oh, we only care about dropping these data points, not these ones over here. But yeah, if there's anything else in particular that anybody has in mind, I'd probably be like a case by case kind of answer.
Okay, thank you.
Okay, now something that we saw in this microcredit example earlier was that not only did we have these parameters that we were learning, the theta naught and theta 1, but actually we didn't sort of care about both of them. We really cared about theta 1, which was the microcredit effect. How much did microcredit help people? And so you could say that's a quantity of interest here. So we're not reporting the whole theta, just a part of it. So an example of a quantity of interest would be exactly this. We take one element out of the full theta vector. Here, let's call it P. So P was 1 in our example before. Another example would be if we care about statistical significance, we'd actually take theta hat plus or minus 2 standard errors. And there could be other quantities as well. Okay, so up to this point, like this, what's on this slide should be considered a review of your intro machine learning course. By the way, if this doesn't feel like a review or you haven't taken intro machine learning course, I will direct you to my own YouTube videos for literally our MIT intro machine learning course at the end. So hopefully this can be more familiar. But if you've taken that, this hopefully feels very familiar. And so now I'm going to start changing things up. So in particular, I'm going to start imagining that we have a weight for every data point. So data point 1 gets a weight of size 1. Data point 2 gets a weight W2 that has size 1. Data point 3 gets a weight W3 that has size 1, up to the nth data point, capital N, which again has size 1. So every data point gets a weight of size 1. We can collect that vector of ones in an all ones vector called Wn. Sorry, called one sub n. Okay, So that's our original problem, that everything gets a data weight of size 1. And you can imagine when we drop a data point, that's like taking one of the weights from 1 to 0, the corresponding weight. If we drop 2 data points, it's like taking each of their corresponding weights from 1 to 0, and so on. And so hopefully you can see that every possible drop data subset corresponds in a one-to-one fashion with a different weight vector W, or that weight vector W is composed of zeros and ones. Okay, so how does this change our problem up at the top? Well, we're going to just slightly change the objective function that we're optimizing. In particular, we're going to pre-multiply each of these losses f by the corresponding weight. And so if the weight is 0, it's like we're getting rid of the loss for that data point because we're not including it. If the weight is 1, we're including the loss for that data point. Okay, well, why is this a useful way to think about this? I mean, in some sense, I haven't changed the problem. I just expressed it in this weight vector way. Well, the observation we're going to make is that this weight vector, when you drop a very small amount of data, doesn't change too much from the all ones vector. And so maybe we can use a Taylor series approximation in it to get a good approximation to what happens when we change W a little bit. Okay, so here, I'm just going to notice, and this will be important to this approximation, that theta hat is implicitly a function of W now. And in fact, our quantity of interest is implicitly a function of W now, because 1, it depends on theta hat, and 2, it might depend on the drop data in some other way, for instance, in the standard error. Okay, so here, the first 2 lines of this slide are just exactly what we had on the previous slide. We have our generic looking data analysis with this weighting of data points idea. We have our quantity of interest, where we notice that it might depend on the dropped data. And our idea, the whole idea of the approximation is let's just do a Taylor expansion around W equal to the all ones vector. And let's do the simplest one. Let's do a first order. I mean, 0th order is, I guess, the simplest one, but it's not going to help us. So let's do a first order Taylor expansion. And if you're interested in higher order ones, ask me a question about that later. Okay, so what does this look like? Well, phi of W is what we wish we could calculate. This is our quantity of interest for this particular drop data subset, because remember, a drop data subset corresponds to a W vector. We wish we could calculate this for all of the billions and billions of W vectors, and we can't because that's too expensive. And so we're going to settle for our linear approximation, which we'll call phi super lin. That linear approximation is just going to be exactly a first order Taylor expansion. So here we have sort of the 0th order term, phi applied to the all ones vector. This is what you get by running your original data analysis. Your original data analysis is literally getting the quantity of interest at the all ones vector where everything has a weight of size 1. So this is like a sunk cost. You were doing this anyway. This is the extra part that we're going to have to compute. So this is sort of just the linear term in our Taylor expansion. It's got this change in W's times this new thing, this psi n. If you happen to be familiar with influence functions, this might look familiar. If you're not, no worries. We're going to call this the influence score of the nth data point. And it's something that we can compute with modern automatic differentiation tools. So nobody has to sit down and write derivatives. We're just going to get this out from using automatic differentiation tools and assuming a certain amount of differentiability in our loss in terms of theta in particular. Okay, so once we've done this approximation, this all sounds well and good. It's a nice approximation, but okay, what do we have to do and not do at this point? We don't have to rerun our analysis billions and billions of times to get all the phi w's. We only have to run our analysis once to get the phi of the all ones vector. So that's great. We've reduced from 10 to the 53 data analyses to 1. So that's a boon. But if we want to calculate phi lin at each W, that's still phi lin at 10 to the 53 W's. That's any computation 10 to the 53 times is not doable. So we still need to ask, okay, how do we take this all the way to approximating dropping data? Why does this actually help? Okay, so let's take this one more step. So remember, what we really want is this exact change. We want to say, what is the change we get from dropping data relative to the original problem? We're approximating it with this linear approximation. And why does that help us? Well, this linear approximation takes the following form. So you can just see this from the Taylor expansion on the line above. All I'm literally doing is just rearranging that Taylor expansion formula. Now, Wn is either 0 or 1. If Wn is 1, this term goes away. And if Wn is 0, we get negative times the influence score. Okay, so this suggests an algorithm. And the algorithm is as follows: compute all the influence scores. So that's a linear time operation in the number of data points. So that's much more doable. Sort the influence scores. This is technically an n log n operation. If you find that sort is truly the bottleneck in your data analysis, I would just love to hear that. I feel like that's not usually the case, but I'm super curious. And now start removing the largest. And so this is how we're going to calculate. Remember, we wanted the maximum influence perturbation. The largest possible change we could get by dropping at most 100 alpha% of the data. And so this is how we're going to get an approximate maximum influence perturbation. We're going to take our sorted influence scores. We're going to get rid of the first one, the biggest one. We're going to get rid of the second biggest one. We're going to get rid of the third biggest one until we have removed at most 100 alpha% of the data, the most that we can. And then we're going to ask, what's the approximate change that we got? So that's the largest, that's the approximate maximum influence perturbation. Now, when we did that, we could record what were the data indices that we dropped along the way to get this approximate maximum influence perturbation. We'll call that the approximate most influential set. We also wanted a perturbation-inducing proportion. So now we can get an approximate perturbation-inducing proportion. That is to say, we're going to remove our largest influence score, throw it out, and then we're going to ask ourselves, did we achieve a certain change, like a change in sign? If not, we'll remove the second largest one, throw it out, and ask, did we achieve a change, like a change in sign? Then we'll remove the third largest one, throw it out, and we'll ask, did we achieve a change, like a change in sign? And we'll keep doing this until we either run out of data, in which case report NA, or until we achieve that change. And that'll be our approximate perturbation-inducing proportion. Now, for the purposes of using our software or using this idea, you don't actually have to understand any of this approximate stuff. You just have to understand the notion of a maximum influence perturbation, a most influential set, and a perturbation-inducing proportion, or whichever one of those you actually want to use. The approximate ones are what we'll actually report and how we'll actually get those results to you. But you can just use the software by understanding the basic ideas. Okay, so let's go ahead and see this in action. Now, before I show you some real data analyses, I'm going to look at a simulated data analysis in order to notice that misspecification and heavy and light tails are just not decisive here, unlike other types of robustness. So for instance, if you were thinking about like cybersecurity style robustness, where somebody comes in and messes up your data, it's a different type of robustness that obviously matters for certain applications. But for a lot of scientists and economists, it's not that somebody's coming in and like adversarially messing with their data. It's that like you can actually have a lot of things go wrong with your analysis without having, you know, an actual adversary, like an actual spy out to get you. And that's what we're getting at here. Okay, I'm just going to describe this at a very high level, but let me first note, why does anybody do simulated analyses? Like sometimes I think people think like, oh, simulated data is nothing. Like, why doesn't everybody just work on real data? Well, simulated data is really important here because it's only in simulated data that we can make sure that our model is perfectly specified. And so in every other case, it is definitely the case that models are misspecified. And so you might think that misspecification is what's driving things. And here we can check that that's not the case. Also, we can check the tails of our data. We can control the tails of our data by simulating our own data sets. For instance, we can make sure that, you know, actual data has Gaussian tails, or we could, you know, have some other type of tails. But this is the only way we can really control those tails. So in this case, what we're going to do is we're going to actually have a perfectly specified model. We're going to let it have Gaussian tails, and we're going to vary the signal, the strength of the effect, and the noise. So a way to think about this is suppose I have a simple one-dimensional linear regression problem. The signal is the strength of the effect. It's like, you know, how much is microcredit hurting somebody or helping somebody in this particular simulation? I can make that really, really big to make it a really easy problem. I can change the noise to make this a harder or an easier problem. So for instance, if I have my x's, my independent variables, very spread out, this is an easier problem. If I have my noise term really huge, this is a harder problem. I can make it so huge that it swamps the effect. And so I can change how easy or hard this problem is. I can change the signal to noise. And we see exactly kind of what we want to get out of this analysis. If I have high signal to noise, if I have an extremely stable result, something where the signal is absolutely dwarfing The noise, I have to remove many data points under our metric, or I get an NA to change conclusions. That is to say, this is a very stable result. If I got slightly different data, my result wouldn't change. And we find that when there's low signal to noise, that it only takes removing a few data points to change. And this is something that you should be aware of in most analyses. If you have an analysis that, there's not much signal there to begin with, you're, searching for a needle in a haystack, and it's a needle that doesn't even matter, and there's just nothing going on in your data, then maybe you don't want to overly convince yourself that there is. You want to check that it's just a really unstable result, and you just happen to get the data that you got, and it doesn't really mean anything. Okay, so let's talk about a couple of more real life data analyses. So first, let's look at this Oregon Medicaid study. So this case, we're going to see that a small p-value is not decisive. So this is a very famous study. You probably read about it in the news at the time, if not more recently, from Finkelstein et al. 2012. There was a lottery in Oregon, and the winners were able to sign up for Medicaid. So this is a really natural way to have something like a sort of natural randomized controlled trial where people could see if signing up, the ability to even sign up for Medicaid could influence people's health outcomes, or if signing up for Medicaid could influence health outcomes. So they look at both in this study. I'm just going to briefly mention one aspect of the effect of lottery on health. They also look at a lot of different health outcomes. One of those health outcomes, again, just for illustration, is to look at after 1 year, so 1 year after they had the ability to sign up for Medicaid, what was the number of days of no impaired activity over the past 30 days? So this is one measure of health that they looked at, and they all kind of look something like this. So they had over 21,000 data points. On the face of it, this is a huge amount of data in the social sciences. It's very hard to get this data. It's worth noting it's survey responders. So we definitely expect that this is the case with missingness not at random, and that we would care if a few data points were driving our conclusion. They found P was less than 0.01 for a positive effect. This is the kind of thing like in the news, it's, if you're reading the news, it just says like, wow, they found this relationship, it was a really big deal. If you were reading a paper, you'd be like, gosh, yeah, P less than 0.01, that's a really killer result. But it's worth noting that we find that dropping 11 data points, so that's less than 0.05%, not 5%, 0.05% of the data changes the significance of that result. So you can go from a very significant result to a non-significant result with just a few data points. So it seems like this is a case where we really see sensitivity. Okay, let's look at another cash transfer study. So here, we're going to see that analyses can be robust. There's some sense in which it's natural for me to focus on cases of non-robustness just to show what this can turn up. But of course, we see many cases of robustness as well, and so I'll show that. And also, we're going to see that removing outliers isn't a panacea. Okay, so this is from Angelucci and DeGiorgi, 2009. It's another very famous study in economics. And there are two conclusions that we're going to look at here. So one conclusion they have is that the direct effect of cash transfers for poor households increases household consumption. So this is another measure of like how much do cash transfers help people. One way of measuring how much it helps people that we looked at before was business profit. Here we're looking at household consumption. Now, a really interesting aspect of this study was they looked at this idea of a spillover. So the randomization here in the randomized controlled trial was on the level of villages. Now, only the poor households in the village got the cash transfer, but you could ask, well, do other people in the village benefit when the poor households get the cash transfer? And so you could look at the non-poor households in the same village and ask, was there a spillover effect? And that's what they did in this study. Okay, so if we look at the poor households conclusion, there were over 10,000 data points, and we find that this is pretty robust. You have to drop over 4% of the data to change the sign, to change the significance, or to change both. Again, there's some point at which you are dropping enough data to change these. We're only really concerned, we only think something is not robust if you have to drop a very, very small fraction of the data to change conclusions, and that's not the case here. Now, I want to note the reason that you see a range, 4 to 10%, is because there's a lot of different conclusions we're looking at here. So one is sign, one is significance, one is sign and significance, and it varies from one to the other, but they're all very high. So this is all very robust. On the other hand, let's look at the spillover study. Here there were over 4,000 data points. The original analysis tried to remove outliers. In particular, it deleted households with consumption greater than 10,000 units, so the ones with the largest response. And certainly this is the kind of thing that you see in a lot of cases. People are trying to be like uber robust in some way, they Windsorize, they do something like that. And we just find that you can still be sensitive. So in particular, even after the deletion of these households with large consumption, we find that you can drop 3 data points to change the significance of the result. And in particular, just a little bit of a brief notion of why this might be. We showed that in linear regression, the influence score, the thing that's driving, which data points we're dropping in this metric, is the residual times the leverage. So if you're only getting rid of outliers according to the residual, the leverage could still be having a really big effect. And so that's sort of suggestive of, why, at least for this notion of outliers, you might still be seeing sensitivity.
Tamara?
Please.
Question. Was there some intuition for what was special about the most influential points in these studies upon manual inspection?
That's a great point. I really need to get a plot of that or something. So on the face of it, I don't have a great answer for this. But I think what I like about this question is that it's absolutely what you should be doing, when you see this kind of result. What we certainly imagine that people should be doing at this point is, okay, I found my influential data points. I found these data points that really mattered for this result. Now what I should do as a data analyst is go in and look at them and pick them out and say, what is special about these? What's going on here? I guess we have a little bit of a notion here in this notion of the residual times the leverage. So certainly we find that the things with large influence score have large residual times leverage. And so you see that in plots. I don't know if I have too much more I can say beyond that, except to say, yeah, this is the plot that one should make for sure. And that ability is available in our software, again, to pick out these data points and then use them. And so maybe I'll use that as a segue to say that I would love for you to try this out and tell us how it goes. We've had a lot of interesting stories from people trying it out so far, telling us that they were finding robust or non-robust analyses, and we would love for you to be one of those people. Okay, so today I showed you this metric to check if there's a small fraction of data that you can drop to change conclusions. And so we have all of this information up in a preprint on the archive. Some of it gets very technical, but again, you don't have to understand those points to use this. You just have to get the idea of, what are we trying to get with the maximum influence perturbation? And those ideas are reviewed in the paper, so I'll encourage you to check that out. Something I'll just mention, because many of you may be from more of a machine learning background, is this is a paper we're submitting to an economics journal. And so this is an alphabetical authorship ordering rather than a typical authorship ordering where I would really emphasize, say, my postdoc in what we were doing. But again, it's been fantastic working with my postdoc and also our collaborator, Rachel. The code is up here at this GitHub repo. So R. Giordano, again, this is my postdoc, Ryan Giordano. If you have any questions about it or any trouble with it, we would love to hear. We've been fielding some of those questions already, and they've been great. They've helped us improve the repo, and I'm sure if you had more, we would find that to be the case as well. So definitely, don't hesitate to reach out and email us, even if you just run it successfully and find some results. We'd love to hear. And then I'll make 2 final sort of aside comments. So one, I just thought it was really, really amazing throughout this, how much we were able to replicate all of this work in economics. I think that's a sign of a discipline that is just doing fantastic work. And I think that we could have more of that in artificial intelligence and machine learning in general. So actually we wrote a note in Nature Matters Rising in 2020, towards the end of 2020, about transparency and reproducibility in artificial intelligence and how we don't see this. And a lot of work, for instance, in medical AI, and in other areas of AI. And I guess I just want to suggest that I think we should. I think this is a really great thing to have. And then finally, if, again, any of this was not immediate to follow, especially the parts about the loss, I have all of my intro ML lectures from last semester. So last semester, I gave the lectures for our Introduction to Machine Learning course at MIT 6036, and they're all up online if you're interested. Thank you.
Thank you, Tamara. I just have two more questions that have come in, if I can give a few minutes.
Please.
Can you give more intuition about what leverage is?
Yeah, so in linear regression, this is particularly easy. I mean, in some sense, we were talking about response being really unusual, far away from maybe a best fit line. And leverage is sort of like the x-axis, the independent variable, being really unusual from a best fit line. And so if you have an x value in your linear regression that's very far from the other x values, there's a very strong pull to that point when you're trying to do something like ordinary least squares. And so that point is said to have a high leverage as a result. Now, somehow the intuition is really easy in linear regression. When you get away from linear regression, it's harder to say something so nice and pat. But that's kind of what's going on here. So again, I don't want to suggest that like things are not related or could not be described as outliers in any sense. Like certainly if you defined outliers to be the things with high influence scores, these are all outliers. But one, it's worth noting that if you come up with a definition of outlier, typical definitions of outliers often ignore the thing that you are trying to do. Like they are maybe not goal aware. And so here we're specifically having that in our influence score, the goal is encoded in the likelihood. And so what is a particularly influential point can vary depending on what you're trying to do with it. A really simple example of this would be if you had multiple covariates or features and you only use some of them for one task and some of them for another task. Obviously, whether they are meaningful is going to vary. And so certainly we see that in a more subtle way here. But that gives you at least a little sense of what's going on with leverage, hopefully.
Awesome, thank you. And then our last question, sort of related to a prior one that was asked, can this methodology be used to recommend what data to collect to make analysis more robust? Sorry.
Yeah, it's an interesting question, and actually one that I think a number of people think of, and it makes a lot of sense. You know, like there's some sense in which, you know, we want to guard against this type of non-robustness for a lot of cases. And so we could ask ourselves, well, how do we do that? And one might be in the data collection procedure. Something that I think makes this challenging, I hate to say that anything's impossible because I feel like, you know, somebody could come up with a super cool idea that I just wasn't thinking of. But one thing that I think makes this challenging is that the nature of our approximation very much depends on observing all of the data, because all we're doing is sort of perturbing the observed data points. We're like letting their weight go from 1 to 0 and imagining that as some kind of continuous value that goes from 1 to 0, but that weight is times the actual observed data point or times the loss at that observed data point. And so it does seem like there's something very fundamental about this methodology that relies on having seen the data to begin with and then changing it, which I think has relationships to other cool ideas. And you know, we've done some ideas in CS like core sets, where you also like weight data points and find a subset of weighted data points, but like somehow it's related to what is the data you have. Turning that into a way to reason about data that you haven't seen sounds tricky on the face of it. Maybe it would be relatively easy if you just had a choice between 2 data points, although I'm not totally sure how things would go there. But certainly if you had a sort of arbitrary set of choices, for instance, of like what covariates to collect next, it's not obvious to me what to do on the face of it. But it's an interesting question, and I think it would be interesting to pursue.
Awesome, thank you so much. And I just want to thank you, Tamara, for presenting to everyone today. And thank you everyone for attending. If anyone has any questions watching this on our website later, please feel free to reach out and we'll make sure to connect. So thank you again, Tamara.
Thanks everybody, and thanks for having me out.
All right, have a good day, everyone.